And hi, welcome to yet another video of kinematics. I'm going to call this kinematics 3. Okay. Hope you have enjoyed the video series so far. Okay, so the last video we talked about how, let's say, if you have a varying speed, how do you calculate distance? Okay, the principle is on a speed versus time or velocity versus time graph. You will, what do you call that? You will just take the area under the graph. We also talked about, okay, if the area under the graph is kind of weird or strange, what we can do is to chop up the graph into many small parts, like this. Okay. Just a minute, my pen is not working. Okay, hopefully this resolves it. Now my pen's working again. Yeah, so we section up the graph into many different parts. We chop it up and then we kind of just take the area of all these small little trapeziums. Okay, and the smaller we make this time interval delta t, the more accurate this area under the graph actually is. And if you make delta t go so small that it goes to 0, we call this taking limits. Then we arrive at something called integration, which is the exact area under the graph. So we repeat this summation process many times in order to get the area under the graph. Okay, now when you start learning physics, oftentimes you will not get this, but it is good to understand the concept early on so that when the real math comes with integration, it won't be so scary. Now let me just give you another very simple example, because the last time I talked about using area under the graph, I talked about, okay, when the plane is going to take off, it needs to hit some threshold speed, okay, and how you can calculate the length of the runway, okay, or estimate the length of the runway, assuming you have constant acceleration. And with the constant acceleration, you will get to the certain threshold speed after a certain amount of time. And then you can use this area under the graph technique to actually see how much distance you actually travel till then. With this distance, you can then kind of plan out how long your runway needs to be based on this constant or average acceleration. Okay, or rather this constant acceleration. Now, if your acceleration is going to differ over time, we don't use this s equals to half at squared formula. Okay, we will just take the area under the graph. Okay, now I want to talk about, just give you one more example in a landing case. Okay, so in the landing case, what happens is that the plane will descend. And then what will happen is that you will go on the runway. Okay, the wheels will come out. Okay, I'm drawing it really badly, but the long and short of it is that the plane will be sort of level like this. Okay, and oh yeah, basically don't worry about the notes. I have them on GitHub. This is called it's under my GitHub called Physics Learning. Okay, link is in the description. It's the Physics Learning, and all this is under the kinematics lectures. Okay, you will see this PDF file, kinematics1.pdf. At least for this video, this will be the PDF you need to look for. So if you want to download from GitHub, you do not need to know how to code. Though GitHub is normally a place to store code, all you need to do is just download the zip file right here. Download the zip file and then you just download it to your PC, extract it. You will be able to find the PDFs that I'm making now. Okay, now back to lesson. Okay, so this plane is going to have some initial speed. Okay, again, let's denote this initial speed using the x direction, because I'll just say this is the x direction. So I call this ux. This will be the initial speed. And what the plane will do is that it has to start slowing down along the runway. Okay, it'll start slowing down along the runway until it goes to a stop. Okay, until it goes to a stop. Over here, ux, if we really stop the plane, we will have ux equals to 0 meters per second. So how long does your runway need to be? Okay, same principle, we use this area under the graph technique. Of course, we need to find the acceleration, because we are slowing down the plane, so this is actually deceleration, or otherwise known as negative acceleration. Okay, negative acceleration, otherwise known as deceleration. Okay, so again, what is the threshold negative acceleration that we can, tahan? Okay, I should not use tahan, but okay, tahan is a colloquial slang we use in Singapore. Is for saying how much can you take, what's the tolerance. Okay, so how much can you take? So I'll just say tahan. Yeah. Okay. Pardon me for using Singlish. Okay, I'm just more comfortable with that, honestly. Okay, so how much acceleration or deceleration can you tahan until you reach this end of the runway? Now we can set based on the comfort level of our passengers. Okay, maybe 1.4 meter per second square is okay. Well, we use 1.4 meter per second square before. Maybe 3 meter per second square. Okay, tolerable deceleration. Maybe 3 meters per second square. Okay, of course you can adjust this value. Okay, you can adjust this value as and how you like, and the runway length will differ, but let's just use 3 meters per second here. So I'll say AX equals to minus 3 meters per second, minus because it's going in the negative X direction, whereas the velocity is going in the positive X direction, or the plane is going in the positive X direction. So again, how do you calculate the length of the runway? Okay, again, always draw a graph. It makes your life easier. So this is Vx. Okay, sometimes in physics or engineering, we use U to denote speed. Sometimes we use V to denote speed. Okay, why do you use that? Okay, at least from a vector's perspective. Okay, if let's say you have the velocity, it's very common to have the x component of velocity, or rather Vx. You just write it simply as U. Vy. It's very common to write the y component as V, and the z component of velocity in 3D, it will be UW. Okay, so this is in a 3D case. Okay, very common to have this in fluid mechanics, so on and so forth. So sometimes we use U and V very interchangeably for velocity, but just do bear with me, I might use them interchangeably as well. So the thing I want you to take away is, if I use this V or U, both of them, they're referring to velocity. In these few PDF lectures in these few PDFs, at least these lectures on YouTube, I do want you to pay more attention to the subscript here. That will denote what direction this velocity is. Okay, so anyway, that's enough yapping. Okay, time in seconds. Okay, so again, we will have Ux at the start. Okay, this is your initial speed, or initial velocity in the x direction. Then it's going to go all the way down like this until it stops. Okay, area under graph is this. Okay, area under the graph is this. Okay, this triangle here. So what's the height of the triangle? Okay, height of triangle very simply is Ux. Okay, what's the base of this triangle? This is a delta t, right? This is delta t. So what is delta t here? For this constant acceleration, delta t equals to, or rather, let's put it like this: acceleration, okay, equals to delta v over delta t. Okay, change in velocity over time. This is the average acceleration. Okay, so what's delta v over delta t? So the initial velocity is let's see, what's the initial velocity? Ux. So final velocity is 0 because it begins at rest. So delta t is what the base we need. The acceleration, average acceleration will be 3 meters per second squared. Okay, let's just give this a value of maybe 100 meters per second. So we can find what this delta t is. Okay, delta t equals to minus ux over minus 3 equals 100 over 3. Okay, I'm not going to take out the calculator. This is about 33.34. I'm rounding out, okay? 33.34 seconds. You want to round it a little more. 34 seconds. Okay, just a nice number. Okay, a longer runway is better to prepare for in this case, so that your plane doesn't crash into a tree or something like that. Okay, so under these conditions, you need 34 seconds to slow down. Okay, and you need you are starting with 100 meters per second velocity in the x direction. So what's the length of the runway? Delta s equals to, okay, this initial velocity, 100 times 34 seconds, right? 34 seconds equals 3.4 km. Okay, 100 meters per second. Always want to write units as far as possible. 3.4 kilometers. And what did I forget? I forget to times half. Okay, half base times height. So 1.7 kilometers. It's a decent estimate for a runway. Of course, you want to make it longer so that you have some level of safety in case you don't decelerate so nicely. Longer is better, at least as long as you have enough land. Okay, so anyway, the other way you can calculate this, and you will see why I'm doing this later on, is to take this big what do you call that, rectangle. Okay, and then I will minus this area. Okay, maybe I'll use a green color to make it more obvious. I'll minus off this part. Okay, then I will get the blue colored triangle. So why am I doing this? I'm trying to derive a formula that you will actually see quite often. Okay, so I'm going to say delta s equals to, what is this rectangle area? This rectangle area is ux times t. So let's write ux times t. Ux the delta t. Okay, so what's the triangle area? We need to sort of do this, minus half. Okay, minus half. So we are subtracting off this triangle area. So what is this here? This is ux obviously, and then this is delta t. Okay, ux delta t, half ux delta t. Okay, what's delta t? Okay, or rather, what's ux in terms of acceleration? Okay, what's ux in terms of acceleration? We saw earlier, here was your ux, here was your acceleration. So the acceleration equals to minus ux over delta t in this case. Okay, so I'm going to make the acceleration this subject. So ux equals to minus a delta t. I'm going to substitute that in. Ux equals to minus a delta t. That's what the formula says. Delta s equals to ux delta t. And this is the initial velocity, yeah? So minus half minus ax delta t. Okay, delta t and then delta t again. So what do we get? Delta s equals to ux, the time is taken to slow down, minus or plus half ax delta t squared. Here is your other formula for calculating distance under constant acceleration, where you have some initial velocity. S equals ut plus half at squared. That's what you may see in textbooks. Okay, all this is derived from calculating area under the graph. So all these formulas, there are many formulas for calculating distance, but the only thing you actually need to remember is just take the area under the graph. You will be able to derive all these formulas quite naturally. Okay, so I've covered quite thoroughly how to calculate distance, how to so-called, in this case, estimate the length of a runway, and we use kinematics for that case. Hopefully it gives you some motivation to learn what kinematics is about. In real-world circumstances, we use this to estimate the length of a runway. Of course, in terms of calculating what's the acceleration, what's the actual velocity of your plane coming in or your plane taking off, there's going to be a lot more mathematics, but don't worry about that for now. We just want to focus on this kinematics. This is the most basic principles. Okay, so this is kinematics in terms of that. So going back to our initial part. So remember we have this runway, we have the cruising altitude, and we have the landing part. Okay, so that's what we've covered so far. We have not covered the ascent and landing. Okay, we have not covered ascent and landing. So let's use these two cases to so-called go through more concepts of kinematics. Okay, so I'm going to go to this part. Going down. Okay, let's do ascent, descent. Alright, ascent and descent. This is of a plane. Okay, so under descent conditions, okay, this is probably one of the most dangerous parts of aircraft. It is how to descend. That means you're flying at some height. Okay, maybe you are 1.5 kilometers in the sky. You are going forward at a speed of maybe 250 meters per second. How do you land this plane safely on the runway? Okay, how do you land this plane safely on the runway without crashing a plane? Okay, safety is most important. So what a landing is, as far as what I've heard from all those documentaries, again, you have AI, you have Google, you can fact check me on this, but one of the most dangerous parts of the plane flight is the landing, because what you're essentially doing is you're doing a controlled so-called crash. Okay, because anytime the plane's in the sky, yeah, you can land, you can go straight into the ground, fine, but will your passengers survive? And if they survive, will they be happy with your flight? Do they want to come back? Of course, survival is the most important, obviously. Survival is the most important for airlines. So safety is number one, and we hope everyone comes home safely. Okay, so that's the most important. But the second most important thing is your flight comfortable? Okay, is your flight comfortable? So if you're experiencing too much acceleration, okay, you might have experienced this on a plane before. If you're experiencing too much acceleration, you will start having motion sickness. Okay, so let's say you are on this chair again. Okay, I'm going to draw a very badly drawn stick man or what. Okay, you are here. Your belt's there. Maybe there's some tray in front of you with some food. Okay, with I don't know. This is a soft drink. Right, soft drink. Now, what happens if you have too much acceleration? Okay, not only will you feel uncomfortable. Let's say you are trying to land the plane, right? You're trying to land the plane. So the acceleration, okay, you are going, let's say at v equals to 5 meters per second. All right, and or rather, you start in the vertical direction. That's the y direction, right? Vy. Okay, you start at 0 meters per second because you are keeping your plane level. Okay, you're keeping your plane level, so you start at 0 meters per second, but then you want to start decelerating. Okay, or rather you start landing, so your Vy actually goes down, negative, because you're going into the ground. So let me maybe draw a better graph. what this vy t. Okay, let's just say 0 is here, right? To make the graph look a bit nicer. Okay, so 0 meter per second. Okay, again I forgot my units. 0 meters per second. Okay, we start 0 meters per second, then we start wanting to slowly descend. Okay, so you start wanting to descend nicely. Okay, to reach maybe a comfortable descent speed. You don't want to descend too quickly, right? You do not want to crash your plane into the ground too quickly. You want your plane to be slowly edging its way to the ground. Okay, otherwise there's a safety concern. So maybe over here, again I'm pulling numbers out of my head. I don't know what the real numbers are, but maybe 1.5 meters per second minus 1.5 meters per second may be reasonable. Okay, so from going from here to here, your velocity changes. There's a delta v. Okay, there is a delta vy happening within some degree of time. Okay, so what does this mean? When you have a delta vy over delta t, and this delta vy, this change in speed is not 0, you'll definitely have an acceleration in the y direction. Okay, you will have acceleration in the y direction. So initially, you start from zero velocity. Okay, you start from 0 velocity and then you are increasing, right? You are increasing the velocity in the negative y direction. So over here, okay, over here you have a constant, or rather you have negative acceleration because your plane is starting to decrease its altitude. Okay, altitude is the fancy aviation term for height. Okay, how far are you from the ground? Something like that. If any one of you are aircraft engineers, aviation people, you can correct me. Okay, you are decreasing your altitude. Okay, so and then you start decreasing your altitude at a constant rate. But over here, you start from a 0 y velocity and you are starting to go negative. So this part here, there's negative acceleration. Then you go into a roughly constant speed to the ground. Okay, so your plane is descending and you sort of need to stop descending once you hit the runway. You need to stop descending once you hit the runway because you do not want the plane to go into the ground, obviously. So you need to stop descending at the runway, right? You stop descending at the runway and you start to slow down your plane as what you saw just now here. Okay, the plane is starting to slow down. Okay, but before you slow down, you need to land your plane properly first. Okay, so what happens is that you eventually want to reach back to your 0 vy velocity when you hit the runway. So hit runway will be around here, and then it will just remain 0 throughout. Okay, what do you have here? Okay, your y velocity is increasing. You have positive acceleration in the y direction. Okay, so yeah, just by looking at the graph, because the speed is decreasing and the speed is increasing, you can sort of see positive and negative acceleration. Okay, is there a way to so-called before that, what is the effect of positive and negative acceleration? Okay, so you are here, you're having your soft drink, you're trying to enjoy your flight. Okay, and then maybe you are watching some movies. Okay, positive acceleration. Okay, positive acceleration in the y direction. Okay, what it will feel like, okay, because the gravity is like this way. Okay, G is pushing you into the ground. Everyone feels this, but to keep your body in position, your chair has to push back up on you. It's giving you positive acceleration upwards to counteract gravity. That's provided you stay in one place, or at constant velocity. So if you have positive acceleration upwards, this force pushing your body upwards will be stronger. Okay, so it will feel as if you are being pressed into the chair. Okay, because by Newton's third law, okay, you may not have learned this yet, but every action has an equal and opposite reaction. So if you want to be pushed up harder, okay, if you want your body to be pushed up harder, okay, your body has to push harder against the chair, and that's very uncomfortable. So, okay, so basically what happens is that your soft drink soaks, it will feel as if it's being pushed into the table. All right. As long as you're comfortable, that's fine. You don't want to do it that fast. Now, if you do it really fast, okay, this one is a positive acceleration. If you do it super fast, then the force on your body by the chair will be so strong. Okay, if you do it too fast, it can actually crush your body, or at least it will injure you. Okay, so you do not want this positive acceleration when you land to be too fast. Okay, so imagine, yeah, you are doing a high jump or something, and you're falling into the ground after maybe you do a high jump. Okay, after you do a high jump, so eventually you are going down at some negative y velocity, and you hit the ground. You hit the ground, and the ground pushes you up. Okay, the ground pushes you up, and then now your final y velocity equals to 0. Now, if this positive acceleration is too sudden, you will injure yourself. Okay, you will injure yourself, you will injure yourself if this positive acceleration is too large. Same thing on this plane. You cannot have positive acceleration too large. Okay, so maybe a steep gradient like that may not be good. Okay, let me show you negative example. Maybe a steep gradient like that will be very bad for you. Okay, this is too much of acceleration with respect to time. Maybe it will injure you. Maybe something like that's better. Okay, something like that's better, or the smoother the better. Okay, the smoother the better. So this is preferable. It's very comfortable compared to this. This is something you do not want. Okay. Now, how much is too much? Yeah, and then how much is too much? Okay, so maybe we again use the standard thing. Maybe 0.3 G is a comfortable upper limit. Okay, you don't want to feel too heavy when you have this deceleration process, positive acceleration process. Okay, and that may be your upper limit, right? Upper limit. Okay, now in reality, your positive acceleration to make the plane hit the runway is not so smooth. In reality, it may be something like this. Okay, so if you ever travel on a plane, you will feel the moment you land. Okay, the moment you land, you go yeah. Okay, how do I put a sound effect? I don't know. So you will feel yourself bouncing up and down like this. Okay, you will feel yourself bouncing up and down like this, and this is what your real descent is like. There will be a mix of positive and negative acceleration. Okay, nothing is ever so smooth like this. Okay, so how do you make sure your whole way through you do not exceed this? Okay, because at this if your velocity is going like this and you're bumping yourself up and down constantly, like this sine wave or whatever it is. It's not a sine wave actually, but yeah, if you're bumping up and down, okay, this is the real one. The real velocity. Okay, this one's the ideal one. Okay, your real velocity is going to be bumping up and down. Okay, and at all times you do not want it to exceed this 0.3 G as far as possible. Okay, how do you okay, if I give you this graph, how are you going to measure the acceleration? Okay, it's not so simple that you have velocity 1, velocity 2, then you take this 2, and then you divide by the time interval. Okay, so it's not going to be that straightforward. However, the same thing applies actually. So as with integration just now, where we want to find the area under the graph when the graph is very sort of different, we can do the same for finding gradients. Okay, we can do the same for finding gradients, and in this case the gradient is the acceleration. So you see this formula I wrote here. Acceleration in the y direction is the change in velocity of the y direction with respect to time. If you notice, this is exactly the formula for gradient. Okay, so it's vy1 vy2 minus vy1 minus t2 minus t1. Okay, so this is the v2 v1. Okay, t1 and t2 are here. Okay, pardon, my graph is getting very messy, so let me redraw the graph again. Okay, vy meter per second, t in seconds. So let's draw the realistic deceleration. So you were starting at negative, and then you start sort of go your way up to 0, and then you start bumping your way around until it reaches 0. Okay, poorly drawn graph, but hopefully you get the idea of what I'm trying to say. So how do you make sure? How to make sure acceleration? Okay, let me see how long the video is. How do you make sure that acceleration won't exceed some value? For example, 0.3 g. Okay, so and to answer this question, okay, one of the questions you need to ask is, what is the acceleration at all times on this graph? What is the acceleration? This is very bad. Okay, so basically, if you have a baseline, if you see yourself on this plane, and you are experiencing this velocity graph, assuming you know that. Okay, you will want to check the acceleration at each point on this graph, okay, to make sure it doesn't exceed 0.3 g. Okay, so if you want to ensure that this acceleration does not even exceed 0.3 g, you first need to know the acceleration at all these points of the graph. Okay, so it's not just taking this velocity here and taking this velocity here, and then you divide by what? Delta t. Okay, so this is not going to cut it anymore. You need to make sure you know the acceleration at each point of the graph, and you want to test whether it exceeds this 0.3 g. So this is how you ensure that your passengers have a comfortable ride. Okay, how do you do this? Of course, there are things you can do. You can make the pilot, train the pilot so that you won't have this funny velocity graph that you feel very uncomfortable. Okay, so that's one way. But to know even, of course, and then you have to design your plane a certain way so that your acceleration won't exceed this value. And during this design process, you kind of need to test and develop the plane design so that you won't exceed this 0.3 g. So maybe your first plane design is really bad. Okay, your first plane design is really bad. So you kind of want to know how bad your plane design is so that you can make improvements. What you need to do is, well, you need to measure the acceleration again at each point of the graph. So that's what I'm trying to say. If you want to make sure that your acceleration doesn't exceed this value, you need to do a lot of testing, design and development as is done in the real world. And when you test a new design, you need to measure what is your acceleration that your plane is experiencing. So to measure this acceleration, at least from this velocity graph, what can you do? Okay, so what can you do is basically this gradient technique is not going to cut it. But I said we can use a similar approach to just now. Okay, so let's say I want to find the acceleration here. Okay, maybe instead of v2 being here, I can say v2 is here. Okay, pardon me. I can say v2 is here. Okay, so this is the first delta t, but I don't want it so big. Maybe I'll have this. Excuse me. I'll have this v1 and v2 being my two velocity points. This becomes my delta t, and acceleration is v2 minus v1 over delta t. That will sort of give you a good guess for all the acceleration upon this part of the graph. Okay, so that part is easy. That part's fine. You can still use, hopefully, this kind of gradient formula. What about here? How about here? How do you find the acceleration at this point? Okay, so where is your v1 and v2? Well, the way you can do it is that maybe this v2 is here, this v1 is here. You take this two, you plug it into your acceleration formula, and you'll get a pretty close reading to what this v2 is. Okay, that is a guess. That is a good guess. But how about make it even better? Okay, to make it even better, we apply the same principle. We make our delta t go to 0. Okay, so yeah, I'm going to take 2 points here, v2 and v1 here. I'm going to take these two velocities. I'm going to measure the time where these velocities are measured, and I'm going to plug it into my acceleration formula. Okay, so in general, let's say the acceleration in the y direction, what I'll do is I'll have a delta vy over delta t, which is vy2 minus vy1 over t2 minus t1. This is your gradient formula. However, if you want the instantaneous acceleration, this is what you're probably more interested in. If you want to prevent a very bumpy ride, you are more interested in this instantaneous acceleration. What you do is you take this delta t and you make it as small as possible. Even better, close it up to 0. So when you have this acceleration, it becomes delta vy over delta t, and you take the limit. Okay, or maybe I shall write this like this. This is the proper method, a little bit more proper mathematically to write things like this. Take the limit where delta t goes to 0 of delta vy over delta t. You will get the instantaneous acceleration. Okay, the shorthand to write this is dvy dt. This is called differentiation. Okay, it's called differentiation. Basically, it's just a very fancy way of saying I'm finding the gradient at one specific point. Okay, so if I find a gradient here, I will take this v here, just a little bit adjacent to it, and I'll take the delta t, and I'll, of course, shift the points closer and closer. Okay, I may start from here. Well, this is a good guess, but I'll try to shift it closer and closer to the point where I'm interested in finding this instantaneous acceleration, and then I will find the gradient there. That is what differentiation is about, when you close this delta t as far as possible to 0. Okay, so how do you do this? You don't use area under the graph. You just try to read these 2 points. For example, if I'm finding the acceleration here, I just read these 2 points as close as possible to here, and then I will take the T1, T2 and T1. I'll read off this. Let's see, green. Okay, I'll read off this delta Vy. Delta Vy. And then there's a delta T here. This will become my acceleration near to this point. However, of course, the best way you don't read off is not to read off the graph manually. you try maybe use some computer program. It will estimate it better for you. Okay, that's the principle. Okay, that's the principle of how you calculate acceleration from this velocity versus time graph, and that will help you then to so-called figure out, hey, am I giving to myself too bumpy a ride with this plane ride? Okay, then I can provide appropriate feedback either to the pilot or to the design crew. Please design me a new plane, or pilot, please fly better. Okay, you need to improve your flying. You were giving your people a very bumpy ride. Okay, so the thing you do is to look at this velocity time graph, and you take the gradient at these very small intervals. Okay, if you make this interval so small it becomes 0, that is what we call the differentiation process. Okay, so okay, one more thing I would like to share. Okay, one more thing I like to share is one example of a derivative. Okay, I want to give you an example of a derivative. Okay, let's say y equals to a t cubed. Okay, a t cubed, or rather this number can be y equals to a t n, where n is some integer. Okay, n is some integer. Okay, and I'll say positive integer. Okay, how to find the gradient? Gradient at any point in time. Okay, what you do is this differentiation process. Okay, I'm going to show you y equal the gradient is delta y over delta t, and what you do is to limit this delta t to 0. This is dy dt. Okay, so I'm going to demonstrate for you. This may take long. If you are not interested, you can skip this, but this is what I'm going to do for you. Okay, let's have some original speed or some original y value. Okay, which maybe I will give you v. Yeah, I'll give you v. So this one actually looks a little bit more like acceleration. So I have at to the n. Okay. Okay, I have at to the n, and it's taken at time t. So I want to say, okay, at some time t plus delta t. Okay, this t is the change in time. Remember, is just look back at the graph. I have t1 and t2. I have t1 and t2, and t2 equals to delta t plus t1. Okay, so this t plus delta t is actually t2, right? So that's why I have this t plus delta t here. Okay, and then what is the so-called v over here, or velocity? I can say it's a t plus delta t to the power n. Okay, so this is fine and all. You will get a t plus delta t to the n minus a t to the n over delta t. And what I want to do is limit delta t goes to 0. Okay, let's go to the next page. A t plus delta t to the n minus a t to the n divided by delta t. Limit delta t goes to 0. Okay, so how do you deal with this thing here? We use something called binomial expansion. If you're not sure, please go and use AI, Google, do whatever. I'm not going to explain it here. I know you'll probably need some advanced, a little bit more mathematics to do this, but in essential, we use binomial expansion. Okay, binomial expansion, what is it? So binomial expansion is, if you look at online, if you look online, binomial expansion may look something like this: x plus y to the power n equals summation. This is a summation sign, and k equals to 0, and k, this is the binomial coefficient, x n minus k, and then y to the power k. Okay, so what does it look like? So let's say n 0. Okay, let's write the first term is k equals to 0. Okay, so I'll just write it out for you: x to the n, because k is 0 here, and then y to the 0. This is just 1, so I'm not going to write that yet. Plus n, so n choose 1, because it's not n choose 1. Okay, but this is the binomial coefficient, x to the power n minus 1, y. Okay, this is a k equals to 1. Okay, next one, we have k equals to 2. So everywhere you see this k here, you substitute with k equals to 2. So n 2, x n minus 2, y to the power 2. Okay, so you dot all the way through. There are many terms like this. We only need to worry about the first 3 terms in this case. Now, if you're not sure about binomial expansion, please go revise some of your math. Okay, this is important in this derivation of how to do differentiation. Okay, this is a derivative. Okay, this is just an algebra example. Okay, so you have these terms. Okay, how do we apply this binomial expansion here? Okay, I'm not going to teach you binomial expansion. Please go and look at some other video. Maybe whatever other video you can find online. There are many videos, okay, nowadays. So I just want to zoom in, assuming you know all this. Okay, what I'm going to do with this binomial expansion is that this y here is actually, well, surprise, it's actually delta t. And then x, we'll replace it with t. Okay. Right. I also forgot to explain to you what these are. And this is the binomial coefficient. We use something called factorial, and factorial over k factorial n minus k factorial. What's factorial? Okay, factorials. Okay, just a quick recap. Factorial is just multiplication in like descending order, something like this. So 3 factorial. 3 factorial is 3 times 2 times 1. 5 factorial is 5 times 3, 5 times 4, sorry. 4 times 3 times 2 times 1. Okay, 1 factorial, it's already at 1, so it's just 1. Okay, then this one's a special case. 0 factorial is also equals to 1. Why? I don't know, it's just like that. Okay, I didn't do mathematics as a major, but this is what it is by definition. So let the mathematicians tell you why. Just for engineering, or at least for this basic physics, just take it as 1. Okay, so if you have 7 factorial, it's 7, 6, 5, 4, 3, 2, 1. You multiply all of that. Okay, so that's what factorial is about. So this term here actually has all these factorials 1, 2, and 3. So that's all we need to worry about. Okay, so n 0. Okay, let's just figure out what these are. This is the first binomial coefficient, n factorial over k factorial. K is 0, right? 0 factorial, k n minus 0 factorial. Okay, this one, thankfully, this one doesn't give you a 0. It actually gives you a 1. So n factorial over n factorial, just 1. Very easy. Let's do the first one. N factorial over 1 factorial, n minus 1 factorial. Okay, 1 factorial is 1. N factorial over n minus 1 factorial. that's just n. So 6 factorial over 5 factorial, that is just 6. That's the example. Okay, so that let's do the third one. Before I go back to there, I think I skipped a lot of steps in explaining why we only need the first 3 terms, so I'll get back to that in a while. Okay, this is 2 factorial n minus 2 factorial. So this is what? n minus 1 over 2. Okay, after that we don't really need to worry. Why is that? Okay, why is that? Okay, the answer will become apparent when we substitute these two into our binomial expansion. So now we can write t plus delta t to the power of n, and this delta t is very small. Okay, we want to bring this to 0. Okay, but let's expand this out first. So the first term is actually t to the n. Second term is n t minus 1. Okay, and then you have a delta t. Second term is n minus 1 over 2 t n minus 2 delta t squared. Okay, plus dot dot dot. Okay, the thing is that when you take delta t goes to 0, okay, and you multiply this delta t again and again and again, then all these other terms will kind of just disappear. You can kind of ignore them. Okay, there's a proper way to do this. Okay, there's a proper way to do this. I don't want to just haphazardly do this, but this is the idea. Okay, so for now, let me not do this. Let me not cancel these terms out first. I will just use the dot 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 notation to say there are many more terms there, but I will want to show you why we can just ignore them in a while. Okay, so let's substitute this back here into this this formula. Okay, let's go. So t plus delta t to the power of n minus t to the power of n. What I'm going to do is I'm going to factorize the a out because there was an a before. And then at the denominator, there's a delta t. So, okay, let's write the first term. Okay, a, okay, t to the power n plus, excuse me, t to the power n. Okay, then you have n, t, n minus 1, delta t, plus n minus 1 over 2, t, n minus 2, delta t squared, plus dot dot dot, minus tn. Okay, pardon my fractions are all over the place, but all these will be divided by delta t. Okay, so immediately what you can see is that, okay, this delta t and this t to the power n actually cancels out. So that's nice. Okay, so all the terms here can be divided by this delta t. So I'm going to do this. N tn minus 1. Okay, plus n minus 1 over 2 tn minus 2 delta t plus dot dot dot. Okay, and basically as you keep increasing your binomial expansion, the powers of delta t, that means this very small delta t, it will get bigger and bigger, and the more times you multiply this small delta t, the smaller the terms get. So that's why things like this you can actually cancel to 0. Okay, but let me just do one more thing before I concretize, before I tell you why it can really just disappear. Okay, remember the whole idea of differentiation is to bring this delta t to 0. So I have shown you the whole gradient, sort of this gradient. When you bring this delta t to 0, it will reduce to this form. And the thing that all of these terms have some power of delta t. Okay, they have some power of delta t. Okay, but it's not a zero power. And when you bring this delta t to 0, this becomes 0, this becomes 0. Okay, what you're left with is this a times n t n minus 1. Okay, so that's how you derive these derivatives for polynomials, or basically this basic algebra. Okay, datn dt, okay, d a t to the power n dt equals to a n t n minus 1. So we have used this binomial expansion thing to figure this out. Now this is more of a mathematical thing, but it's one of these examples to show, if you look online for common derivatives, you'll get this formula. But I wanted to show that just by this idea of taking limits, getting smaller and smaller gradients, you do get the same answer. Okay, provided of course you have the correct mathematical tools like binomial expansion. Okay, at least for this case. Now, not all the differentiation you can do it so simply like that. Okay, or maybe for some of you it may be quite complicated already. I'm bringing a lot of complications there, but basically this is how derivatives come about. Okay, you're taking gradients like that, and you are making the delta t so small that a lot of these terms just disappear, and then you are left with some final answer right here. So that's what doing derivatives is all about. It's just taking gradient, okay, at a certain point in time. Okay, so I've shared with you roughly what derivatives are. Okay, it's probably quite a lot for some of you, but I just want to share this with you so that you understand what derivatives are about. Why do these happen to come into kinematics? Okay, so hopefully this gives you some context to all the math that you are doing. Yeah, so I think I will just leave it as that. And of course, I wanted to share the real life plain examples so that you understand, hey, kinematics is not just something you blindly follow, something you just put formulas. There are real world applications to kinematics. Okay, for example, a plane landing. Okay, I think that's all I have to share for tonight. I'll see you next time. Thanks for watching.